Thanks, sir.
Leo does want to know.
Can't talk now till it.
Yeah, I did that with George a lot.
Shmuel Fishman was a postdoc at the same time. I know.
I saw him. I was in Israel. So happy that he was still around.
And I mean, who else was there? I mean, Novid, yeah, it was earlier. I mean, it was slightly past the really exciting renormalization group time, I think. Yeah.
Finding the last few.
What did you work on there?
I was actually doing superfluid helium. John Neppy.
Yeah. I really remember that.
Effectively like a low density.
Yeah.
Developed a theory of dilute, crossover behaviors, those gas, fully reactive.
So it was Vinay Ambagoakar was there who was working on that sort of stuff, and was he or no?
Two-dimensional dissipation, dynamics.
Yeah, yeah. And Eric said, yeah.
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 Yeah, again, temperature boost.
Oh yeah, it was a big deal, wasn't it? Yes, that's right. And Ben Whittam, who's still going, isn't he? Still, right? Yeah, and he was giving a very good talk, not while he was still 90. Yeah, yeah. That was amazing. He did Cork, in his 90s, and it was a good talk. It was, yeah, he was great, and also kind. Just a nice man. Yeah. No, it's pity we lost Michael. And it sounds like it was pretty horrible at the end. I mean, I don't really know, but I don't know much, but I get the impression that he wasn't really up to anything for the last few years. He never seemed to really bounce back from that at all. Yeah, that was tough. Yeah.
No, that's what's the static energy. That's right.
What is it you do now?
Well, I work for a British company, BAE Systems. American end of it. It's aerospace. They have a research arm in Burlington, and it's mostly what I would call an electrical engineering kind of department.
Yeah,
A lot
yeah.
of software, artificial intelligence, that sort of thing. There are things that physicists can do. So I do a lot of work on. I do a little bit of fluid dynamics on the side, kind of thing.
Yeah, I mean, we all need to think.
Mostly remote sensing, a lot of remote sensing. Far, radar, sonar, water stuff. So very small scale, there's projects, microchip integrity.
Okay, yeah.
Trying to scan this microchip coming from China somewhere. Anyway, so all sorts of stuff.
Yeah, so you have to know everything.
I've learned a lot about the
Yeah.
ionosphere.
Yeah.
Over the horizon.
Yeah, yeah. That's good.
Pretty far from phase transition.
That's right. Phase transition is a bit old hat now, if you ask me.
You don't hear much about realization.
Everyone's trying to do the third or fourth. Well, everyone's trying to find the third or fourth value of a significant figure in alpha, and it's really boring, if you ask me. In the old days, when it was a pattern and you had to find the pattern in the underlying physics, it was great. But I think anyone who's, there's not much at the moment. There's not much else to do. So it's best to move on when things get hard.
So tragically, Kim Saul. Yeomans, one of our organizers, happily stepped in.
Happily?
Happy to have a set of so she'll be talking about that, about active Nematic. She's the head of the real file system. A lot of time off. Discovered she was a postdoc. Interesting, almost overlap. I arrived.
Okay, thank you very much. To just get used to the idea of sort of changing roles a bit here. So I'm going to talk about active nematics. So a little bit more on active matter, but I think I'll probably do it in a very different way than the lectures you'll have from Yahui next week. So unfortunately, I'm going to be gone by then, but I think it might be interesting to see what the broad field and how many different directions you can look at it from. I'm going to particularly concentrate on active nematics, and in this audience, active turbulence. And this lecture is going to be introducing active turbulence and starting to explain the equations and the physics behind it. I think we understand active turbulence in the same way that one understands inertial turbulence. There's still a lot to do to actually get a proper theory of what's going on. So let me start by waffling a bit and talking about why I think active materials are exciting and the sort of reasons that I think you can sell this subject for. So what is active matter? Well, active particles take energy from their surroundings and they use it to do work, usually to move. And they do this on a single particle level. So each of the particles individually is taking energy from its environment and it's using it to do work. Yeah? Oh, okay, yeah. But questions are great. Okay, so what it isn't is a fluid which is sheared, because then everything is moved from the outside by some sort of external forcing. What it is these individual particles, things like cells, things like bacteria or motor proteins, which are taking energy, usually chemical energy, and then using it to do something, often to move. And we're talking about a complete range of length scales here. I'll be talking about motor proteins, the engines of the cell. I'd be talking about cells and microswimmers, and then all the way up to us, we're active particles, but we're just too hard for anyone to do theory on. So we'll mostly talk about the very small. And I should emphasize that we're really changing length scales from Tiffany's lecture. She was talking about big, and I'm talking about small. And when it comes to hydrodynamics, we're talking about low Reynolds number. So let's take these particles, let's take a load of microswimmers and put them together 2D layer so we can see what's going on and see what happens. And that's what happens. A state which looks like turbulence and has become known as active turbulence. And the real turbulence people, the inertial turbulence people, hate that because to them, turbulence is something with Kolmogorov scaling. And this does not have Kolmogorov scaling. It is not turbulence in the technical sense. It's turbulence as in it's like a waterfall with everything moving around all over the place.
What was the time scale?
That would be probably a second or so. Yeah, these things are tiny. Yeah, and they move about a micron per second. So they're micron-sized particles. Yeah, it's about 10 swimmer lengths. That's probably the way to think about 10 swimmer lengths. The vortices are a size of about 10 swimmer lengths. Okay, and it's not just swimming things which do this, yeah? It's turbulent in the sense of chaotic, yes. Well, I mean, well, I think it's probably me that was the problem of actually calling this turbulence. But to me, I mean, someone on the street would call that turbulent. Yeah. But we'll talk a little bit more about how much it's turbulent. And probably by tomorrow's lecture, I'll get to a stage where it does do something like inertial turbulence for reasons which I don't understand at all. So I think that was one thing I particularly would like to talk about at this school in case anybody else understands it. Okay, so this is, let's see if I can get that to move again. This is, again, a type of tiny animal, a bacterium. This moves by twitching. It holds onto the surface with these little feelers, and then it moves by pulling itself along, and it actually moves forwards and backwards. And so it's a little bit different because things are not swimming. They're actually moving on a surface. But again, you get this chaotic-like behavior. I'm now going to jump a little bit and talk about motor proteins, molecular motors, the engines of the cell, because I want to introduce another example where you see active turbulence and one that's been used a lot experimentally. Okay, so how do we move? All right, so you're taught that muscles make you move. But actually, something I never thought about till about 10 years ago, but it's such an obvious question. What makes your muscles move, right? What's the sort of really low-lying cellular level way of getting stuff to move around the body, of getting processes to happen in a body? What are the engines of the cell? And the answer is these motor proteins, and they're really very clever. You have to move stuff around the cell, right? You're going to have to move proteins from one place to another so they can do something. And if they were just swimming, you've had it, because cells are tiny. Brownian motion is important. And so if these things were trying to swim from place to place, they'd be thumped by all sorts of molecules on either side, and they'd never get anywhere. So what the cell does is it lays down tracks called microtubules, which are basically just polymers. It's able to lay them down, and then it's able to take them up again, so it can use the monomers to make them in different places. And then these amazing proteins called motor proteins move along the tracks. And many of you will have seen this. This is the microtubules being laid down and then being unlaid down. And then this little thing here is a motor protein trotting along the tracks, pulling its backpack, this vacuole, which is full of relevant proteins as it moves along. So the first time I saw that, I said, oh yeah, load of rubbish, but it actually is almost like that. These things have been designed to work in that way. It's not quite so efficient. It's a much more stochastic process, moving backwards and forwards. Let me play it again. It's a nice movie, isn't it, while I'm talking? Okay. The physicist version of how it works, all right, ignoring all chemistry, is basically it works because the protein has a certain shape. It's a shape that acts a bit like an elastic band. This thing is fixed down, so its 2 feet are sitting on the microtubule. A molecule of ATP comes in and joins the back foot. That makes the back foot detach. Then because of the shape of the molecule, that makes it a little bit elastic, and the back foot tends to flip forwards. So it's more like front, and then it waves around doing a random walk until it actually grabs hold of the microtubule in front. When it does that, it releases a molecule of ATP, and that makes the back foot, the new back foot, ready to gain a molecule of ADP. So that's, yeah, sorry. Oh gosh. I ought to know that. I think these things could, I mean, my guess is these things will move about a micron per second, okay? And step length is of order 10 nanometers. All right, you can work it out, maybe out by factors of 10, but that's the sort of thing. This is just a vacuole, it's called. So, and the answer is I don't know exactly what it is. I'll look it up, or you can look it up to find out. I should know that. Any chemists in the audience who know that? Right. But what, and people sort of understand how these motor proteins work. I mean, I gave you the physicist version. The chemists understand very well the transitions between energy levels which make this work. What I think nobody really understands is the sort of control theory of how the cell works out, how it wants to lay down the microtubules, how it wants to work out how many motor proteins it has walking along each microtubule, and then how it sort of works out how it grabs hold of one of these vacuoles and moves it along. Okay, I think there's an absolutely amazing question there, which certainly I don't know much about. And if any of you know more about it, I'd be delighted to hear. This is just to show you that it's not just computer simulations. This picture here is, these are those 2 feet, and coming downwards is a function of time. And so what you're doing is you're moving, you can see it jump, this one here in particular, jumps from one place to another. And so you're actually seeing, you can't see it actually move, it does it too quickly, but you're seeing the steps here. Okay, sorry, downwards between there and there. Just to show this is just like microscopy.
And the scale is nanometer scale?
Each of these little motor proteins is about 15 nanometers. Yeah, so that will give some idea of the step length. Okay, so I mean, I like talking about these because I think they're nice, but also they form the basis of one of the best experimental systems out to look at fabricated active matter. And this was invented about 10 years ago now at Brandeis by Zvonimir Dodik. And what his group did is take these microtubules and take them out, actually the brains of cows, I think. So any vegetarians don't listen now. All right, so you've got these microtubules and you put them in a suspension with motor proteins. And they're special 2-headed motor proteins. So these motor proteins can attach to the microtubules on both sides. Okay, so these microtubules, these polymers, the motor proteins attach on both sides. And they have a directedness to them. So when they walk along the microtubules, they're going to sort of push the microtubules downwards. If you have 2 microtubules like that, bridged by these motor proteins, if the motor proteins are both moving up like this, if both heads are moving together, nothing's going to happen. However, if you have the ones on this side walking up and the one on that side walking down, what it's going to do is it's going to push the polymers relative to each other. And so you're going to get these things pushed around by these motor proteins. And it's pretty boring until you add PEG, which makes this very dense. And if you add PEG, what you find is the motor proteins are pushed around and you get a system which again looks very much like a chaotic-like state, which looks again a bit like this active turbulence. So this is microtubules being pushed around by motor proteins. Ah, yes, now that's sort of the next sentence, right? It's not quite chaotic, right? There is some sort of structure there. These dark regions are structures, they're actually sort of holes. These are actually bundles of these microtubules of the sort of white stringy things you're seeing. And you sort of get these holes, and if you're a liquid crystal person, you might recognize what they are, and they're going to come and turn out to be important. But I'm going to come to that in a bit. You know, so lots of different sorts of this chaotic behavior. Are they all the same? Yeah?
Doesn't look like they generate small.
What happens is you get a sort of polarity sorting, because some of them are being pushed up and some of them are being pushed down. So you tend to get bundles. And then what happens is the bundles sort of buckle and bend around. And what you're seeing is these bends. Yep. These bends form, then they sort of grow, and the whole thing becomes a sort of dynamic mess. Yeah. Oh, that's a very good question. I should have said. Everything I'm talking about today is two-dimensional. Luckily for us simulators, all the experiments are in 2D. And that's because it's much easier to visualize things in 2D. Much more recently, maybe in the last 2 years, people have done 3D experiments with this stuff. Talk about that later. Yeah. Essentially, it's just to make it more concentrated, because you need this to be a dense suspension for this to work. No idea, sorry. I mean, that is something which is known to compress things. So I think it's what you try first if you're a chemist and it worked. I think it really is like that, yeah. Okay, yeah. That's chemistry. I think it's complicated chemistry, which is to do with the shape of the molecules on the it's a biased random walk. So it's not perfect, but it's a pretty good walk. But I'm sorry, I don't know the details of the chemistry, but it's the chemical interactions between these things. Yeah. Yeah. Yes. Yes. Oh, pleasure. You're going to see lots of videos like this. I hate these. There's a scale there which is 50 microns. So I would say the microtubules is of 100 micronish, of order 100 microns. Yeah.
When we see like one continuous tree, it's many microtubules.
Yes. Yes, they tend to be this polarity sorted. So all the ones which want to move that way get together and form one of these bundles. Yeah, and then they sort of break up. Yeah. Yes, yes, because it's going to be like a liquid crystal, which has elasticity. Right. So again, this is really just a sort of, isn't nature wonderful? Just for fun, really. This is another of these motor proteins. It's called the bacterial flagellomotor, and it lives here, and it turns the tail of the bacterium so the bacterium can move. And again, this is an artist's impression. And I did look up the sort of, this is a slightly old one. I did look up the newer one, and it's not so different. So this will do for our purposes. Here's the length scale for those of you that are keen, quite rightly, on length scales. Each of these little things is a different protein Pretty amazing, right? How does the cell put that together? How does it organize itself to actually create an engine like that? This is a movie where people have tried to answer that question, but this is not a movie which is backed up by reality. It's just something which might work. It's a sort of fun movie. But the point I want to make is that this is active self-assembly. It's putting together an active system. And as physicists, we really, really would like there to be a generic principle which enables complicated structures like this to form. I'm not convinced there is. It might be just that evolution has had a long time to get it right. But it's very clever to make something this complicated. And as people try and make tiny robots, we can't do anything as small or as good at that as that yet by a long way. So it's very clever. And then again, of course, we have active matter on a larger length scale. I'm going to claim that the physics of these tiny active systems is all, at least to 0th order, the same. Nobody's quite sure what happens for these larger systems where you have flocks moving in a collective way. Is this fluid mechanics, or is it the things looking at each other and saying, look, we're all swimming in this direction, let's get on with it? But there's some amazing patterns here. You'll have seen similar amazing patterns with these starling flocks. And people really do not understand how this works. This is a dolphin. I thought it was a shark, but probably it wasn't if those people were there. But I got told it was a dolphin. Yeah. But I mean, that patterning there is just amazing, isn't it? Why it happens. I don't understand why that happens. Nobody really understands why that happens. How you get these patterns, how these things decide. For example, when the dolphin was going like that, all things went like that, right? Why? Starling flocks, right? You've got these lovely shapes. So they're almost like two-dimensional layers which curl around. What's the physics? And people have done some really nice theories, some based on superfluidity, some based on hydrodynamics, some based on the things, actually having sentient, looking at each other. But no one knows the right answer. They're very hard simulations because these are inertial things, okay? Yeah, so I'm going to tell you the physics behind what happens for the small ones, but I don't know, I can't do that one. Don't know, don't think anyone knows. Yeah, yeah.
So do we observe consistency in patterns?
For the microscopic ones, all right, there's consistency, and I'm going to tell you about how I write down the equations, and I'm going to do it properly, all right? I mean, at the moment, this is just waving my hands around and saying why I think it's exciting. For the macroscopic ones, I don't know what's going on. And I suspect there isn't enough data for those, but it's certainly not where I'm an expert. Right, so just to show you that, just for completeness, really, a fabricated system which is active, people can make active colloids. So what they do is they take colloids. Colloids are tiny particles, usually about a micron across, and they stick this hematite, which is the blue blob on them. The hematite, if you put them in a solution with hydrogen peroxide, I have to write down the names of these wretched chemicals to remember. All right, what happens is that if you shine on light, the hematite reacts with the hydrogen peroxide and creates tiny bubbles, which basically push these things and makes them self-propelled. And so what you can get is a very simple form of pattern formation. The colloids are self-propelled, they come together and they make rafts when you put on the light, okay? And then when you turn off the light, they are going to just do Brownian motion, and they're going to essentially melt the rafts.
What those hematites which are inside the cluster, they also react with the
that's one of the problems with these active colloids, that as soon as you sort of surround them with each other, or if you have too many of them, you run out of fuel very, very quickly. Yeah, yeah. It's with these ones, I think it's essentially a diffusive-phoretic gradient around them, which tends to push them. That's normally what happens with the chemical ones. But the simplest way is that you get a sort of basically a flow of force pushing them forward to make them work. That's not a very good way of saying it. A lot of them with the chemicals, if they react with chemicals, if half of them react with a chemical, you get a gradient of the chemical around the edge. That gradient sets up a diffusive-phoretic flow, which pushes them. Oh, the clustering is just that if you have particles which are self-propelled, they will cluster because they'll come together and they'll just basically get stuck. And then the next lot will come and join them. So it really is just a...
They come to a cluster, they can bounce off the cluster.
Yeah, so the... Right, because they're not elastic, they're just tiny spheres. So why should they bounce off? They're still being pushed. As long as they're hematites outside, they're still being pushed towards the cluster. Yeah. I think here it would just be related to the density, how many particles you have. All right.
Related question, if you wait longer, you use proportionally more and you get larger crystalline, or remain dilute?
I think that will depend on parameters, on exactly what sort of system you've got. I've never seen them do more than this in this system, but people have done all sorts of different systems, some of which form tiny clusters, some of which will completely form one cluster, and it's very much parameter dependent. Okay. So what makes active matter special? Why am I showing you all these different pictures of strange things that happen? And the answer is that it's out of thermodynamic equilibrium. That's the big different thing about it, all right? You are taking energy from the surroundings and using it, and you're doing it the whole time. So you stay out of equilibrium. And actually that's what living systems are, right? We're all out of equilibrium because we always have to have energy to do things. It's really bad if you're a living system and you come to equilibrium. You just don't want to go there, right? And in fact, Schrödinger knew this. He said, living matter evades the decay to equilibrium. And that's a really nice way, I think, of thinking about living matter, all right? It's always out of thermodynamic equilibrium. That's what makes these systems special and different. No detailed balance. So why do I think it's interesting? Well, first of all, you're out of equilibrium, and so you're doing non-equilibrium statistical physics, and that's hard. And active systems have given us a playground to see the sort of things that can happen in non-equilibrium statistical physics. If you're an engineer, it would be nice to create tiny engines, like these micro engines in the cell, because they're very clever and they're very efficient. And increasingly, I think people have seen this link between active matter and biology. I mean, it was sort of there rumbling around in the background for a long time, but now really it's taken off, possibly because of the new biological experiments people can do. Can we use the theories of active matter to describe what's going on in biology? And that's sort of probably, if I get that far, probably that's what the third lecture is going to be talking about a bit. And that's very new. I mean, I think it's only quite recently that that's taken off. Okay, so all we're going to focus on now is active turbulence. I've shown you these pictures. Let me see if I can get them to move again. We've seen active turbulence in swimming bacteria. We've seen them in this microtubule motor protein mixture. These are cells, eukaryotic cells. Those are the squishy ones plated on the surface. Again, you get this turbulent-like behavior. Is it the same for all the systems, or is it really very different? All right, can I write down a generic theory of active turbulence? Because being a physicist, I can't remember more than one thing at once. So it's sort of easier if we can. So that was waffle, really. So what I'm going to do now is actually get on with it. I'm going to try and talk about active turbulence and active topological defects. So there are two bits of sort of background. And the first is a little bit of low Reynolds number hydrodynamics. Now you'll get this really nicely, I think, from Tom Powers when he gives his lectures, but I think it won't hurt to have a little bit twice. And we've heard a lot of really nice high Reynolds number things. So this is just to show you that things are different at these length scales. Also, I like the pictures. All right, and then I'm going to talk about nematic liquid crystals. Could you put up your hand if you know what a liquid crystal is? Okay, in that case, I'm going to talk fairly quickly about liquid crystals. We've got enough soft matter people here. Then we'll introduce the active stress, the extra stress you have in these fluids because you have things swimming about in them. We'll talk about active topological defects, and then I'll talk about maybe some examples of where you actually get active topological defects in nature. And then, depending on where we get to, these things at the end are going to be the other lectures. We'll see what we end up doing. All right, so I'm used to audiences that really don't know very much fluid mechanics, but do know loads about soft matter. So we all know about this, don't we? All right, that's the Navier-Stokes equation. And we're going to look at very small length scales. So we're at low Reynolds number, where the viscous term dominates over the inertial term. So we're starting with this limit, right? Not these wretched high Reynolds number people that start with their nice high Reynolds number limit and then use the viscosity just to get out of problems. Okay, and here's Reynolds. This is Reynolds doing his experiment. They did really nice experiments in those days. Okay, so he looked at Puscher flow in a tube, so flow down a tube. And the modern version is just to look at, so the tube is sort of this big thing here, and this is a line of dye in the middle. The Reynolds number is going to change in the top right-hand corner. And this just shows you what happens as the Reynolds number increases. And what we know is we expect a transition to turbulence. There you can see you're starting to get it. And as you rank up the Reynolds number, you get vortex formation type things, and then a more turbulent phase. We're right at the beginning of that. We're looking at low Reynolds number flows where everything is smooth and flowing. We're going from high Reynolds number where you get loads of vorticity, where everything is very chaotic. This is inertial turbulence, proper turbulence. And what we'd expect at low Reynolds number, okay, things are much more gentle. So this is a really nice picture of Volvox, which is a little animal, which is about, oh, what's happened? I didn't like my movie. Slideshow, slide. Okay, it's about 100 microns across, and these things are just swimming around nicely, and the dots show you the background flow. So now I'm going to show you the famous low Reynolds number movie. Okay, just in case anyone hasn't seen this, because this is how to understand zero Reynolds number flow. we're forgetting about the inertial term. We're just left with the Stokes equations, okay? Just the Navier-Stokes without the nonlinear and the time-dependent term. And let's see if I, oh, sorry. See if I can get this to work. I have to do it by hand, that's it. Okay, this is low Reynolds number hydrodynamics. And I don't think I understood low Reynolds number hydrodynamics until I saw this movie. Okay, so what people are doing here is just putting dye into this beaker of a high viscosity fluid. Okay, I'm saying it's low Reynolds number, and you'll see people's hands around, and it obviously isn't microscopic length scales, but they're getting away with it not being microscopic length scales by having a very high viscosity fluid. And so this is very, very low Reynolds number. You have to do this gently or the diffusion mucks you up. Okay. And then you get your graduate students to hold it down. And you're meant to count how many times round this goes. I'm sorry, it does go on a bit, this movie, but you have to build up the suspense. Okay. And if I try and move it on, I get in a mess because I end up, we have to go back to the beginning. So it's best just to wait. I think it goes around 7 times. Okay. And then back again. Okay, at 0 Reynolds number, flow is reversible. Okay, if you go forwards in time, then do exactly the same thing backwards, you will get back to where you started from. That's what's special about flow at 0 Reynolds number. Yeah? I don't know, actually. Help. Is potential flow reversible?
Potential flow would be reversible and irreversible. Potential flow is about being gradient of potential at a given moment of time. It tells you nothing about the flow. It would be reversible or irreversible.
Okay.
What you see here is not only a very low Reynolds number, it's a very high speed number. It's a very low diffusivity.
Oh, yeah, yeah. Yeah, yeah. Diffusivity, I mean, this blurring is diffusivity, and you've got to ignore diffusivity. But it doesn't have to be that high, this Schmidt number, I don't think. I mean, a normal fluid will do this. Yeah. Okay, so there are 2 consequences of this which are important for what we're going to talk about. The first one, I'm not going to say very much about, just to say that it's a consequence, is that swimming at low Reynolds number is tricky, because if you're a little swimmer and you try and do breaststroke or something, you go like this and you happily move like that. And then you try and carry on with your stroke and you just move back to where you started from. Okay, so if you're a tiny swimmer, you need your swimming stroke to be different forwards and backwards in time to break the reversibility, to break the reversibility of Stokes flow. And the way these tiny swimmers do it is by having tails which have waves going down them, because waves give you a direction in time, or maybe have, some of them have little corkscrews, because chiral corkscrews have a direction in time. So that's why tiny bacteria are this funny shape. It's a desperate attempt to swim and break the conditions of low Reynolds number. This is the scallop theorem. However, for my, and this will be Tom Power's story probably, yeah. For my story, we need to know something else about this low Reynolds number flow. And in particular, we need to notice that the Stokes equations are linear. Because the Stokes equations are linear, we can write down a multipole expansion for the Stokes equations, an expansion in powers of 1r, which work a long way away from the swimmer. We heard about a multipole expansion for the Laplace equation yesterday. This works in exactly the same way, except I'm solving a slightly different equation, so the form of the multipoles is different. Let's just look at the equivalent of a single charge, which is just a single force. So consider a tiny colloid, a point colloid, if you like, being pulled through the fluid by a force. What sort of flow field does it set up? This is a picture of the flow field that it sets up. Sort of makes sense, doesn't it? You're pulling this thing, so the flow is going to move like that. And this flow is called a Stokelet. And I've written up there the form of a Stokelet. The velocity is just the force over 8 pi times the viscosity times something which basically is a 1/r dependence. All right, so just like a charge has a potential which goes as 1/r, Stokelet has a velocity which goes as 1/r. Yeah.
What is the tangential boundary? The transverse one, the normal one.
It's a proper tangential no-slip boundary condition. But what I am doing here, remember, this is a far field.
I'm wondering, like, if the surface is there split but not.
It's no slip. It's a proper no slip condition, which is really one of the reasons it's very different from the ideal fluid. Yeah. What I've written here for a Stokelet is it's a singular point, in fact. But if this was really a little colloid, right, what I've written there would be right, but only a long way away because it's only the leading multipole. But I'd have to solve it with no slip boundary conditions. Yeah. Okay. Actually, working out the Stokelet is non-trivial. It's not hard, but it takes 3 or 4 pages of algebra. Okay, so you have to go and look it up in a book once, and then you've done it, and then that's your Stokelet. Okay, so what about a little swimmer? What is the far flow field of a little swimmer? What does that look like? Well, swimmers can't have forces acting on them. Oh, sorry, can't have unbalanced forces acting on them, right? Because they're autonomous creatures, and there's no one there sitting there and say, come on, you know, pulling it along through the fluid. It has to move by exerting equal and opposite forces on that fluid, right? That, if you like, is a definition of one of these micro swimmers. At any point in the forces are equal and opposite. So if you want to work out the flow field due to this thing, you have to add up a Stokelet from one force and a Stokelet from the other force. And what you're going to end up with is a dipole, which instead of going like 1/r, goes as 1/r squared. Just the same as if you have charges, a plus and minus charge, right? The potential goes as 1/r squared instead of 1/r, because you basically lose that first order term. So let's do that at least in hand-waving way. I'm adding up a Stokelet from this thing and a Stokelet from the other side as well. And what you end up with is an answer like this. Okay. The 1/r squared makes sense on the bottom. The force times the distance between the force, the FL on the top, is like a dipole. The 3 cos squared theta minus 1, you have to do the calculation, and that's what comes out. And what does it look like? And there's the answer. The thing on the left is one of these dipolar flow fields, and the thing on the right was just the colloid. The thing on the left is a dipole. It goes as 1 over r squared. The thing on the right is a colloid. Yeah. Yes. It has to go, and the swimmer is going like this. It's pushing the fluid like that at any time. How does it move? That's a very good question. And the answer is, remember what I've got here is the far flow field. Okay, so what I'm talking about here is the far flow field. What determines whether or not a swimmer can move is the near field. And it's got to overcome the scallop theorem. So then you have to ask, how can it overcome the scallop theorem when it can only do equal and opposite forces? And there's rather a nice little story of a model, which is a model 3-sphere swimmer, which answers that. This can move. What it has to do is it does that as its first step. Okay. Let's see if I can remember how to do this. And then it does that. So this one in, and then that one in, and then those two move outward, and then those two move outwards, right? So then I should have got back to where I was before, but there is an imbalance there. And the reason is that when these move in, that one is in a different position than relative to these two than when those two move in. When those two move in, that one's still out. When those two move in, this one's closer. So it's that rather subtle imbalance, which means that it can move. But if I looked a long way away, then the flow field would look like 1 over r squared, because I'm sort of averaging over time. Yeah. I hope I've got the right arrows. Yeah. So your low Reynolds numbers of force is proportional to velocity. No, because there's no net force. So you actually need these. You can't do this with a pair. Yeah. Yeah. No, you're okay. I mean, you but you just it's because you're at 0 Reynolds number, right? If you turn off the force, you immediately stop. And having a pair of forces is like, yeah. Yeah, yeah, it's because we're at low Reynolds number, right? The force at one point in time is like the velocity at that point in time.
Make a force, another force backward, and not to be in the same place. You need to make a circle with the space. This you need at least to produce.
Yeah.
It's actually gauge with theory.
It's if you just have forces doing that, again, you're just fall foul of this reversibility. So I can't do that story if I just had a pair doing that and then doing that. They would move, but then they would move back the same amount. Yeah. No.
Forces velocity, how do I know how much energy?
Oh, good heavens. The first one, the answer is no. It's extremely difficult to find out. You just have to solve it. and actually do the solution, because you know the velocity field that each of these is making, because it's the Stokeslet. Yeah. Working about energy, I'm going to have to think about that one because that's complicated. Okay. Quite where energy comes in when you're at actually 0 Reynolds number.
If you choose direction, then you decide whether on the left you first turn on the right. You choose the direction of the motion.
That's right, but which direction do you choose? It's not obvious.
Somehow when your two spheres are close together, there's less drag or something.
That's I mean, that's basically the physics. Yes.
The flow field is such you get less drag.
Yes. Yeah.
Third one.
I mean, that's half the obvious. It's something like that. I'm not sure it's exactly like that, because it might be just that the velocity field, quite how the velocity field here on number 3 is what matters. Yeah, but we spent a long time trying to solve this and work out which direction it went. It's not obvious. Not to me anyway. Yeah. Essentially, yes. Yeah. Right. Okay, I think about, I mean, we're at low Reynolds number, so there's no acceleration. So there's sort of no time dependence here. So when you apply a force, you immediately, that force sets the velocity field everywhere. Yeah. Okay. That F is a vector, and that F is giving you this special direction. Yeah. So you're putting it along there. Yeah. Essentially, yes. Then what's confusing you? Yeah. No, because you've got a direction, but also, I mean, it's not electrostatics, because F is a force, and you don't have that force in electrostatics.
It's like the charge.
Yes, yes. And it's because you're solving Stokes and you're not solving I'm not sure of, no, I wouldn't think, I've never seen it written in terms of a potential. Right. Really do. No. No, it's absolutely not. I mean, you're not solving Laplace's equation, you're solving the Stokes equation, which is a vector equation, and that makes a big difference. So the multipole bit's the same, but the formula are not the same.
I don't see it.
No. No, it shouldn't be.
It's a string function field. Rotate by 90 degrees.
Yeah. No. I mean, you actually have to solve the Stokes equation for that thing. And it's not trivial getting that out. Yeah. 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 Yeah, that's right. But I don't think you can here. Yeah, this is absolute.
It's an imposition of 0.
No. So I just don't think it's helpful to try and map it directly onto that. I mean, you can wave your hands around and say this is still a multipole expansion, but the forms of the multipoles are very different. And that's fine, because you're solving a very different equation. So you can't do that mapping sensibly. I solved the Stokes equations with a force which was a delta function at the origin. Yes.
Divergence of B is
Yes. Yes.
electrostatics be the curl of B.
Okay, so that's just satisfied by the pressure.
Yes.
Yeah, that's what the
Yes.
pressure is for.
Yes.
So then you just solve the transfer problem.
Yes.
Essentially, yes. Yeah. It's not trivial, actually. I mean, it's not hard, but it takes about 4 pages to do it.
So now you go for the transfer problem.
You're finding a Green's function, essentially, right? You're finding a Green's function of that equation. Right. But you're not expected to be able to do it in your head. Okay, so we add them up, and this is the dipole field, and this is what we actually need to know, right? That we end up with this, a swimmer has a far flow field which looks like that. These are the experiments. These are from Ray Goldstein's group in Cambridge. Much as I hate to praise Cambridge, these are beautiful experiments. Okay, so this is an E. coli swimmer, actually about several hundred of them, where the far flow field has been averaged over. And you can see here's the dipolar flow field, which is pumping fluid out at the ends and in from the sides. Okay, so far flow field is what we expect. It's a dipole. This is chlamydomonas, which is this thing which does breaststroke. There's a real mess, right, close to the swimmer. But if you look carefully a long way away from the mess, you've got a dipole. It's pumping fluid out from its sides and in from its ends. So it works for these swimmers. There are 2 different sorts of swimmers, okay? The swimmer axis is here. This one pumps fluid outwards from its ends and inwards from its sides. Okay, that's called an extensile swimmer or a pusher swimmer. This one here is the other way around, yeah? Pulls fluid in from the ends and pushes it out from the sides. And that one's called a contractile swimmer or a push swimmer. And these words extensile and contractile is just the sign of the dipole. All right, it's basically where the dipole has forces like that or like that, and turns out to be important when we're looking at active matter. I think that one's a theory, yes. Yeah.
What are they imaging?
The velocity field of that thing. Just PIV. I think PIV. They're very clever experiments because you have to image a lot of velocity fields and average over them. And just to prove that these things are different, if you had a net force, this is this Volvox thing. Volvox is quite heavy, and so it swims up against gravity, and so it has an additional gravitational force on it. So there is a net force, so you don't expect it to look like a dipole, you expect it to look like a monopole, and there we are. For this one, the flow field looks like that, which locally is like that thing I showed when you had just a force on the system. So that sort of all hangs together nicely. All right, and the punchline, the important thing for our active turbulence is that this flow field has nematic symmetry. What I mean by nematic symmetry is that there's an axis which is special, right? Let's picture the horizontal axis, but that way and that way are the same. So it's like a headless vector, all right? So nematic symmetry. This flow field has nematic symmetry, and that's why these things have ended up being called active nematics. And that I have actually said, but just to say it again, depending on the direction of the dipole, you call them extensile, fluid going outwards along their long axis, or contractile, fluid coming inwards along the long axis. Right, any questions? This is a good, more questions? Yeah? Yeah.
I just trying to mention, normally I think precipitation, you lose energy with the Reynolds number don't have Reynolds. So how is energy? I understand at a high level how energy is being lost. You're driving the equation, how I see that actually.
I think, I mean, it's being lost due to the viscosity. All right, it's all being lost due to viscosity. And it essentially, if you force the thing, you immediately, the flow field immediately spreads out. There's no time dependence in how the flow field spreads out. That I believe to be true so far. I'm not sure about the right way of linking that to energy. I mean, I think it's that the energy you put in is immediately dissipated. But let me think about that. It's a good question, and I don't know a good way of answering it at the moment. Yeah. Yeah. Sorry, I didn't hear that. Can you shout? When we talk about active instabilities, which we haven't yet, nobody else knows about them, we're always going to worry about a continuum. All right. So just like in Navier-Stokes, you forget about molecules. When we're writing down the continuum equations, you eventually get, you're looking at the leading order, which depends on the far flow field. We'll come to that more later. Yeah. Yeah. That's right. That's right. No time dependence in the equation. You actually have two Reynolds numbers, if you like, a space Reynolds number and also a time Reynolds number. As long as things go slowly enough, you're okay. But if they go very fast, you'd have to put that in, and it's called unsteady Stokes flow. You put in the du by dt, but not the u dot grad u. You have instantaneous propagation of the flow fields. That's right. And that's what zero Reynolds number means. You do that and you feel it over there immediately. So that's how energy is propagated, but how energy is lost. Right. That was what he was asking. And it's a good question. Well, I don't think I do, so you can tell me.
I'm sorry, the moment you start generating the flow, you introduce shear.
Yeah.
You're not going to see it. But essentially, you have these shears that generate heat, generate losses.
Yeah.
So in order to maintain these shears, you have to have.
That makes sense, but let me think about it and make sure. Yeah. That with the maths of it, yes, yes. Yeah, yeah. But remember, you know, viscosity is what's doing things here. There's no acceleration. Yes. No. Mm-hmm. Good, thank you. Right. Okay, so hopefully that's sorted out swimming at low Reynolds number. This is nematic symmetry. All right, so that thing there is a nematic molecule or a nematic colloid, and it has the same symmetry as the swimmer. And if I take a lot of those nematic particles and I put them together, I end up with it can end up with a nematic phase that they actually want to line up more or less parallel to each other. It's due to a subtle balance between energy and entropy. Okay, and we call this a nematic phase. It has long range orientational order, i.e. if something over here is lined up like this, something over there a long way away is also going to be lined up like that, but no long range positional order. The centers of these things don't sit on a lattice. This is nematics in Oxford. At high temperature, you get the high temperature isotropic phase, and at low temperature, you get the nematic phase. If we have an ordered state, we need an order parameter to deal with it, okay? One possible order parameter is a director. Its bottom's fallen off. It's meant to be a headless vector along this direction. But actually, a much more useful order parameter is this thing called a Q-tensor. The Q-tensor is the order parameter of a nematic phase. I'll just say a little bit about the Q-tensor. If it worries you, the only thing you really have to worry about is just that its largest eigenvalue tells me about the magnitude of the order, how lined up these things are, and its largest eigenvector tells me about the direction of the order. But let's just see how that works a bit. Oops. Okay, so this Q-tensor is an order parameter for the nematic phase. Its definition is Qij is unimportant constant Nij minus delta Ij over 3. These n's are unit vectors in the direction of colloid or molecule I. So it's just a little unit vector along I. I and j are components, x, y, z, as per usual. And this is an average, a local average over molecules in a certain region. So this matrix is a symmetric traceless matrix. Okay, it's symmetric because if I switch over I and j, I'll end up with the same thing. It's traceless because if you think of its elements, its xx element, that's going to be nx squared minus the third. And then if I add up the yy1 and the zz1, I'll have nx squared plus ny squared plus nz squared minus the third 3 times minus 1. And if I didn't say that n was a unit vector, I should have done nx squared plus ny squared plus nz squared is 1. So it's organized to be traceless. It doesn't, oh, you're only allowed one at once. Someone's booby-trapped the back of that. Okay, so let's just look at Q, what it looks like, just because the only way I can really understand what's going on here is actually just writing the bloody thing out and seeing what happens. So if I and j are x, I'll get nx squared minus a third, ny squared minus a third, nz squared minus a third. These terms here, that's nx, ny, right, for the xy one. That one's nx, nz, that one's ny, nz, and then it's symmetric. So it's going to look like this. Okay. So what is that matrix going to look like? Oh, I mean, in Oxford, we've got boards which go like this, and this will go up. So they don't go underneath things when you try and write something. I'm going to have to do it up here, I think. I just want to write this down so as we know what it looks like if I have a fully ordered state and if I have a completely disordered state, because that will show you how it can start looking like an order parameter. Okay, so if I have a completely ordered state along, say, z-axis, all right, nx squared is going to be 0, ny squared is going to be 0, nz squared is going to be 1. These cross terms are going to be 0 because either nx or ny is 0. And I'm going to end up with a matrix which looks like minus a third, minus a third, 2/3, and all these things are 0. And so my largest eigenvalue is going to be 1. Remember, I've got 3 halves out here, multiplying that 2/3. So the largest eigenvalue is going to be 1. The largest eigenvector is just 0, 0, 1. Okay, that says that everything is lined up along the z direction. If instead I have the nematic state, completely random nematogens, what's Q going to be? Nx squared minus a third. Well, in that completely random state, nx squared is equal to a third, right? Because nx squared plus ny squared plus nz squared is 1, and they all have to be the same as each other. So this comes out as a third minus a third, which is 0. That does as well. That does as well. These cross terms are also going to be 0, because if I average nx, ny over a random configuration, I'm going to get 0. And so you can see that the order parameter, the largest eigenvalue, is going to be 0, no order. Yep. And you can't define an eigenvector for that one. So it's sensible that that's an order parameter. Okay. Unimportantly, but just say it, if those two terms are different, what it tells you about is what's called biaxial order. If that's my order along Z, pretty much you always assume that there's no order in the XY plane, and so those two terms are the same. But you could imagine a secondary order along Y, say. That's called a biaxial liquid crystal. People are still arguing about whether they exist or not. The only other thing we're going to have to need about these nematics at this stage is to write down a free energy. Who knows what I'm on about if I talk about Landau theory? Okay, what Landau said was that a simple way to write down a phase transition is to just expand the free energy in terms of the order parameter. So the free energy has to be a scalar. And so if I want to expand it in terms of my order parameter, I have to have indices which give me a scalar. And then the equilibrium state is determined by the minimum of the free energy. And the allowed terms for a 3-dimensional nematic are those ones. Okay. If you don't know about Landau theory, sorry, I'm saying the words, you'll have to go and learn it for a simple magnet first. Expand the free energy in terms of the order parameter, keep enough terms. These are the only terms you can create, which are scalars up to 4th order. Yep. And then minimizing the free energy will give me equilibrium. Yep. LM is the same, it's the same. Yeah. Remember, you've only got X, Y, and Z to worry about. Yeah. And it's a combination of tracelessness and the fact you only have 3 indices. Yeah. 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 Because it's not a scalar order parameter. So you can create this, which you couldn't for a scalar, yes. But also the B is only 0 if up and down are the same. And what this gives you, which is slightly different, is it's a weakly first order transition. Yeah, which is actually, what's more, this is meant to be an expansion for small q, but it works incredibly well, even for large q for liquid crystals. Yeah. Yeah. That's right, but you need a slightly different definition. Yeah.
Q is only uniaxial.
Yeah.
One. one direction. So you need more general that's Q plus a B. E, if you have one direction, that's the N hat. That's the uniaxial N I N J minus 1 to the delta. That's the Q, but then you can also write down, if you think of orthonormal coordinates of N, you need to write down MM minus LL. That's MI MJ minus L. That's the biaxial guy. That's the guy that measures the symmetry of the plane.
Yeah, that's in here. That's in that tensor if you want it to be. By taking the x and y components different. But he's right that if you're looking for hexatic symmetry, sixfold symmetry, you can do something similar but not quite the same. Yeah. Yeah. I think you no, I think you need more. I'm only used to 2D ones where you can actually do it with 2 indices, but I think you need more for more complicated dimensions.
It depends what kind of order you're looking for. If you're looking for quadruple, like nematic order, buy that. That's what you need. But let's say you consider something that has 0 Q, so it looks optically isotropic. But it may have high order, like triad, like Ni, Nj, Lk or something like that. Then that may be not true. So that's like saying this corresponds to angular momentum 2, but you can consider angular momentum 3. So yes, that theory is with the score Q is 0, but then I order 3 in themselves. So you find out where that CIJ. So in fact, the Tommy Bensky worked out that kind of order. If you have like a liquid molecules that are banana shaped like this, imagine that they don't have Q, but they have some time.
Okay, so then what I need to do is worry about what happens if I have a system which has inhomogeneities, if Q varies from place to place. And to do that, you put on an elasticity, which the simplest form of the elasticity is like this. What it says is that this is an amazing thing because it's an elastic liquid that if you muck up your nematic order, there will be an extra energy associated with those gradients. And K is my elastic constant. Okay, and here is a picture, which I think it's nice to see this, right? For example, if you take the liquid crystal and you put it between 2 plates and you splay it and you fix the direction on the 2 plates, you can see that the nematic has a sort of, there's a change in the direction of the nematic order. It's mucked up. There's going to be an extra energy because the nematic order isn't perfect. Similarly, if you fix them to point perpendicular to the plates, the thing has to bend, or if you take 2 plates and twist it like that, it has to twist. This is a liquid, but if you fix the order parameter on the plates, you can maintain these distortions in the nematic order, and so you have to write down a free energy associated with them. And when I just have a single K, a single elastic constant, these guys, I assume they all have the same energy. And usually that's a pretty good approximation, at least for theorists. Okay, good. So to get to the end of this, right. So one of the important things about these liquid crystals is that you can have defects in them where the nematic ordering goes wrong. These are topological defects, and what topological defects mean is that, well, one way of saying it is they have infinite energy because the ordering is going wrong all the way out to infinity. Another way of saying it is that they're like knots, that you can't actually get it right without making changes all the way out to infinity. Or if you want it mathematically, if you take a line integral around the core of the defect, you get a non-value, a non-zero value, which I've called M here, which is the topological charge. We are going to worry about defects in 2 dimensions mostly, at least to start with. There's a whole zoo of these, but the most important ones for what I'm going to talk about for this active turbulence is defects which have topological charge plus a half, which look like comets, which are these red ones, or defects which have topological charge minus a half, which have this 3-fold symmetry. So that's a really important thing to remember, is the shape of those topological defects. And if you have a passive liquid crystal, like in your computer screen, what happens is that these things want to annihilate in pairs. So they behave a bit like electric charges. They move towards each other and they annihilate with each other, okay? And you hope you get perfect nematic order, but you can't get rid of them individually. Okay, so we've all got, everybody okay with topological defects? Right, so now it gets complicated, and I'm not going to go through this in detail. What I want to ask is, how do I write down the continuum equations, the equations of motion for a liquid crystal? So it's the same level as writing down Navier-Stokes equation for a simple fluid, okay? But this is not a simple fluid. It's a fluid which is composed of these nematic molecules or these nematic colloids. How do I write down the continuum equations? The important thing is the equations I've got in the boxes at the top. The rest is just the sort of details for the experts, but it really doesn't matter for what we're doing. It took people a good 20 years to get these equations right. So I think we're just going to take them as read. If you have a complex fluid, big difference is that you need an extra equation which tells you the dynamics of the order parameter. Here we've got the material derivative, which tells me how the order parameter moves. This S is a rotational term, which says that if I have something which is like a nematic, and I have any sort of shear flow, it's going to make the nematic move like that. Okay, so it's just a term which basically takes account of the coupling between the shear and the molecule. And any shear is going to make the molecules turn. This is a phenomenological term, i.e. it's put in as a fudge factor because it works, all right? That H is just the derivative of the free energy with respect to Q. And so what this term says is just what's going to happen is that if the thing isn't flowing anymore, it's going to relax to the minimum of the free energy. And that's what you want to happen, right? This tells me a minimum of the free energy is equilibrium. I need in my dynamics this model A type term, which says that, you know, if you muck it up and then you stop pushing it anywhere, it's just going to relax back to the minimum of the energy. So that's the first equation. It's the equation for Q for the order parameter. Then the other equation I need is one for U, the velocity. And the way I've got it written here, it's exactly looks like Navier-Stokes, right? Usual material derivative on the left, the nonlinear term. That's always going to be very small for these things, because I've said I'm low Reynolds number, is equal to the gradient of the stress tensor. If this was just Navier-Stokes, the stress tensor would be related to velocity derivatives, the symmetric velocity gradient tensor, and that's the viscosity. That's the normal Navier-Stokes viscous term. The extra thing you have in here, okay, the extra thing is that if I have a liquid crystal molecule and it turns, it will set up a flow called the back flow or the elastic flow, if you like. And you have to write that down. And if you write it down, it's horrible. Okay, it depends on Q and the derivatives of the free energy. But people understand it, but it's horrible. And usually it's a fairly small term in these systems. So people understand liquid crystal hydrodynamics. And the question I want to get to next time is, how do we change that so it describes an active nematic? And it actually turns out that these equations don't have to be changed very much. You just need one extra term so you can describe this active nematic. What you need is an extra term which tells you about the extra stress, because these little things are moving around and producing flow fields in the fluid. And it sort of makes sense that this extra stress might depend on Q, because they're making flow fields with nematic symmetry. So I'll tell you what it is. I'll motivate it with a sort of hand-waving argument next time. In a way, we've done that already, right? Nematic symmetry, so you expect it to depend on Q. And then I will try, it's going to be fun, to reproduce the original argument in which was written by Ramaswamy some time ago now. But it's a bit hand-waving, all right? And I mean, that's why it was so brilliant that he understood how it worked, but it's not really a mathematical argument. It's sort of doing the symmetry in a different way. So you're probably going to complain, but that's fine, because yeah. And then we'll actually see how it actually works when we actually solve these equations and get active turbulence. Okay, so I'll finish there, and there's some time if anyone's got any more questions. Yeah. Yes, they're actually lines, and that will come when I get that far. You go around the line, yeah? You've got a line like that, you take a line around it like that. I mean, in fact, sorry, lines is quite the wrong way to say it. They have to close to form loops, in fact, or end on surfaces. Yeah.
Okay, so in a dense system like this, we have the streams. The hydrodynamic interactions between them are not actually like the hydrodynamic passes, so as we see with the Stokes. Like there's a spin, right? Especially because you're at the top of the plate. Instead of like literally like hard like bodies kind of type of hydrodynamic interactions. Is that right? Or there's really a long range hydrodynamic interaction?
There is a long range in hydrodynamic interaction, but you're right. It seems that the screening is not very important in many of these systems, although in some systems it is.
What's
right? It depends very much on the experiments. I mean, the ones I'm going to show you are actually the microtubule motor protein mixtures. And what you have there is that the stuff sits on an interface between two fluids. So it's a very good question, and it matters, but it turns out not to matter that much for at least the experiments that I'm showing you. Maybe these things have sort of thicknesses of about 5 bacteria, and you're okay. But you're quite right to worry. And the other thing is that I'm, very much going to do a continuum approximation where you take the leading term. So I'm going to ignore short-range interactions between these things, and that works fine.
Just one more question. The model of the equation, the gamma is 1 over the relaxation time.
The gamma, yes, there is 1 over the relaxation times. Yes. Again, that's an approximation because you've got a liquid crystal, so you're meant to have 5 different viscosities, but it works. Yeah. Essentially, it's not an integer. Physics is because that and that are the same. Yeah. So if you actually go round it and wave your pencil around to go round it, what you find is that you actually go around half a turn. Right. If you start there on one side and you move around, you end up there where you've gone round. them is a half. You can have defects with charge 1. For example, this chap here is a defect with topological charge 1. Yep. These particular ones are two-dimensional nematics, okay, because you need the nematic symmetry. And they are very well known in nematics. They're, you know, they're all over the place. Yeah. Yeah. Yes.
I just wonder how do you define
the way I define non-equilibrium is that there's a continual flow of energy in the system. So you're in a dynamic equilibrium. The properties don't change, but everything is moving, right? Yeah. So equilibrium would be that it wasn't moving anymore. Nothing is changing. Nothing is changing. Yeah. Yeah. Oh, sorry. Yeah.
White hair guy.
They actually can't even be a nematic. See you next lecture. Oh, so it's how these things respond to the flow, and it basically tells you the difference between how much they respond to vorticity of the flow and how much they respond to shear forces. It's a sort of a technical detail of the equations. But in theory, you can't have a single one because it would have infinite energy. So in a real system, you have them because you have boundaries or defects as in dirt, or you have them in pairs. If you have them in pairs and they are not stuck, what they will do is very gradually move and annihilate. But often they are stuck because the forces for them to move are small.
My colleague Noah Farm, that's the reflective crystal. There's a sample that's 35 years old. That's dislocation line. But you can see with your eye.
Did I have a Hamiltonian? No, I had an H. My H was df by dq. Yeah. And for this one, you will actually. I mean, these equations are not active, right? So these equations will go to a minimum of free energy. Yes, it's like a thermodynamic equilibrium, which is the minimum of the free. And these equations will do that because they're passive equations, i.e. not active. But when I put in this extra term, which I'm going to derive next time, that won't happen anymore. Yes. Yes. I always think of it as you have to count the right number of indices. Yeah.
Yeah, there's no background orientation. So the underlying theory is isotropic.
Mm.
That's why you always want to construct out of schema.
Okay. They come in naturally if you write it in terms of a Q tensor. What actually happens at a defect is the largest eigenvalues cross over. You can sort of see here because there I've got ordering along X and here I've got ordering along a different direction along Z. So that would correspond to the largest the eigenvectors corresponding to the largest eigenvalue crossing over in symmetry. And that's why this is a nice order parameter, this cube, because it's automatically there. What you end up with is right close to the defect core, you get 0 ordering.
I mean, I think your gradient term will cause you to vanish.
Yeah, that's right. Yeah.
Everybody's hungry?
Yes.
Back at you.
Nudge. Mm.